few sessions that we have spent on basic kinematics, one-dimensional motion. Of course, the same thing will get extended to two-dimensional motion, three-dimensional motion. It's not going to be anything different. It's not going to be anything to bother about. But the basic ideas will continue to be these only, the ones that we have learned. It will only be extension of these ideas, or, collating them in various ways. That's all. Now, while we continue our journey with basic kinematics, which will continue even after this session, problem solving essentially, I want to have a quick digression given to you on some angular variables. What we have learned so far are the linear variables. Now I want to get you acclimatized to angular variables, in the sense that suppose there is a particle having a certain trajectory in the xy plane. So this could be the trajectory of a particle in the xy plane. This is the origin of coordinates, and this is the position vector of the particle p as a function of time. Position vector of the particle p as a function of time. At different instants of time, this position vector would be different. If at any given instant of time t, the particle p has coordinates x comma y, then its position vector is going to be xi cap plus y j cap, and so on and so forth. The modulus of r is going to be root x squared plus y squared, which is its distance from the origin. So essentially this position vector takes you directly to where the particle lies at various instants of time, in general a function of time if the particle is moving. While we defined a linear variable called velocity, which measured the rate of change of position with time, we have the acceleration, another linear variable, which is linear acceleration. This is linear velocity, linear acceleration, which is rate at which velocity changed with time. We would now want to have an idea of the orientation of the particle, the orientation of the particle. The orientation of the particle P could be measured with this angle theta. This angle theta could be used towards measuring the orientation of the particle. This will give me the orientation of the position vector. This theta would give me the orientation of the position vector. This theta in general will be a function of time. It's going to vary with time, yes or no? So this theta, which is an angular variable, which we will measure in radians invariably, will be a function of time. There is a rate at which theta changes with time. There is a rate at which this theta changes with time. Which will measure the rapidity with which the orientation of this position vector changes with time. Yes or no? We now end up defining the rate at which theta changes with time as what is called the angular velocity of the particle. Angular velocity of the particle. This is defined as omega, the angular velocity of the particle. Commonly measured in radians per second. d theta is the change in theta, dt is the change in time. So this is the rate at which theta changes with time, which is the angular velocity of the particle, which in general is a function of time. Now this, of course, this by its very appearance seems like a scalar. Where is the vector element here? I'm calling it the angular velocity, but actually the expression that I have written is the angular speed, is actually the angular speed. But then, this has a direction associated with it. The direction of this omega, I'm going to come to this at length in due course, but for the time being, what I want to tell you is, suppose the particle is going this way. Suppose the particle is going this way. Essentially, you take your right hand, curl your fingers in the sense in which r is changing. See, r is then swiveling in this sense, anti-clockwise, isn't it? If the particle is going this way, then r is swiveling this way, anti-clockwise. Yes or no? Right? So, in the sense of the swivel of r, curl your fingers. Watch where the thumb points. And use your right hand, not your left. Watch where the thumb points. The direction in which the thumb points will give me the direction of the angular velocity. More to come on this, but for the time being, get acclimatized to the angular speed. But if the particle were to be going this way, then this position vector would be swiveling clockwise. Curl your fingers in the sense of the swivel of r, the direction in which your thumb points, which in this case would go into the plane of the board if the particle was going this way and the r was swiveling clockwise. If the r was swiveling clockwise, curl your fingers this way, the thumb would go into the plane of the board. The direction of the angular velocity then would be into the plane of the board. If the particle were to be going this way, I repeat, then r would be swiveling anti-clockwise. Curl your fingers in the sense of the swivel of r. The direction of the thumb then is out of the plane of the board. The direction of omega will be given by the direction of the thumb, right? More to come on that, but for the time being, it will suffice if you at least understood that the angular speed of the particle is measured by the rate at which this angular variable changes with time. Now, the theta that you see here, without limitation, say if this is the trajectory of the particle, even though I've chosen this as the x-axis and this is the position vector of the particle, theta is measured with respect to the positive direction of the x-axis, but let me tell you, need not necessarily be. Theta could have been measured with respect to any reference line. This could be any reference line which need not be the x-axis. The rate at which this theta changes, as long as you stay loyal to this reference line, the rate at which this theta changes with time or the rate at which this theta changes with time is going to be the same. You know why? Because suppose this is just any line, L, and this was the x-axis, right? And say this angle is, alpha. Angle between the x-axis and the line is alpha, right? Then do you realize that the angle that r makes with the x-axis is going to be theta minus alpha? The angle that r makes with the x-axis is going to be theta minus alpha. So now, if I differentiate, so this is the disposition of r with respect to the x-axis. Theta is the disposition of r with respect to the line L. And I claim that d dt of theta minus alpha is the same as d dt of theta. Why so? Because alpha is a constant. So if I differentiate this, this will give me d dt of theta minus d dt of alpha. But d dt of alpha is 0. So it does not matter what your choice of reference line is. But stay loyal to that choice of reference line for a given situation. Right? You can measure your angular variable with respect to anything that is any line or any direction which is convenient. Obviously, it makes sense to measure our thetas with respect to the positive direction of the x-axis. That's convenient, right? So there we go, isn't it? Now, and do you all understand, it does not matter whether I measure the angle with respect to the x-axis or I measure the angle with respect to the line L. It does not matter. It'll give you the same value of omega, right? Okay. Now, we also define the rate at which this omega changes with time. This is angular velocity, rate at which theta changes with time. We define what is called d omega dt, rate at which omega changes with time, as alpha, which is angular acceleration of the particle. Which is angular acceleration of the particle. While this is measured in radians per second, this is measured in radians per second squared. As you can check for yourself. D omega is radians per second, that makes it radians per second squared. That's angular acceleration. Clear? Now, can I wipe this off? If there is a situation in which mod of r remains constant, position vector changes, but the magnitude of the position vector remains constant. That means the particle p moves in a manner that its distance from the origin does not change with time. Then the motion executed by p is going to be circular, right? This is the criteria for circular motion. This is circular motion. You know what I'm saying? This is circular motion then. So, if this mod RT means what? Distance of P from the origin. If that does not change with time, that means the path described by P is a circle centered at O and of radius equal to mod RT. And of radius equal to mod RT. Right? If in this circular motion, omega remains constant with time. If omega remains constant with time, then it's called uniform circular motion. If omega in addition remains constant with time, then the motion is called uniform circular motion. Yes or no? Now, can I wipe this off? Say, suppose there is a ladder. This is a ladder, AB. Suppose this is a ladder AB. And the B moves along, the point B moves along the wall while the point A moves along the ground. And the point A, at some instant, let's say, the ladder, say of length L, makes an angle theta with this line. Suppose this was the angle theta that the ladder made. This theta would vary with time. This theta would vary with time. That means the rate at which this theta changed with time could be used towards computing the angular speed of the ladder, right? The ladder would have an angular speed which would be measured by the rate at which this theta changes with time. Because see, the orientation and reorientation of the ladder would be measured by this theta, and the rate at which this theta changes with time would be a measure of the angular speed of the particle, because the angular speed is about how a body reorients itself with time. Or if that's about that's as far as a rigid body is concerned. For a particle, like I said, it's going to be about how it's, there is a position vector of the particle, right? And the position vector makes a certain angle with a certain reference line. The rate at which that angle changes with time would be a measure of the angular speed for a particle. For a rigid body, this is not a particle, but this is a collection of particles. Now, for a collection of particles, how would you measure the angular speed for that collection of particles constituting a rigid body? Again, take a reference line. This could be my reference line, and the rate at which this theta changes with time would be a measure of the angular velocity or the angular speed of the ladder, for example, which is not a particle but a collection of particles. Yes or no? Now, suppose A is being moved to the right with a constant velocity v0. Suppose A is being moved to the right with a constant velocity v0. I now want to be able to calculate the angular speed as a function of theta. I want to calculate the angular speed as a function of theta for the rigid body. Suppose this is the origin of coordinates. What would be the coordinates of the point A? Variable coordinates of the point A. L cos theta 0, isn't it? The x coordinate is going to be L cos theta. Y coordinate is going to be 0. So L cos theta comma 0. Yes or no? Now, what is V0? V0 is actually the rate at which the x coordinate of the particle changes with time. Yes or no? V0 is the rate at which the x coordinate of the particle changes with time. Clear? Right? That means it's the rate at which d dt of L cos theta with time. That's V0, right? Rate A is moving along the x-axis, and the rate at which the x coordinate of A changes with time would measure the velocity of A. So V0 would be d dt of L cos theta. Now L is a constant, so it will wriggle out of the derivative sign. So that's d dt of cos theta. What is d dt of cos theta? Huh? No. That is dd theta of cos theta. dd theta of cos theta is minus sine theta. But dt, right? Do you realize chain rule? This is minus L sine. Differentiate first with respect to theta, and then theta with respect to time, and then theta with respect to time. Yes or no? That's consequence of chain rule. You're differentiating this with respect to time. So what would you do? You would first differentiate with respect to theta, and then differentiate theta with respect to time. Yes or no? Right? So that's, and what is d theta dt? The angular speed of the ladder. So very clearly this is V0, and this would be omega, and the omega of the ladder could be obtained as minus V0 by L sine theta. While theta varies, omega varies. While theta varies, omega varies. Clear? Omega could be obtained from these considerations. Do you all understand this? That's as far as a rigid body is concerned. Clear? Now, can I move? So you know what it means by angular speed of a particle and what it means by angular speed of a rigid body, right? Can I wipe this off? Now, suppose there are two particles, A and B. Suppose there are two particles, A and B. This is the line joining the two particles. And say A is fixed. A is fixed, right? And B moves, say, in a direction perpendicular to AB with a velocity v. B moves with a velocity v, right? Perpendicular to AB. B moves with a velocity v perpendicular to AB. This is 90 degrees. Now, in a small time dt, so initially it's perpendicular to AB. In a small time dt, A is fixed, it will remain here, whereas B will move to a point in a small time dt. B will move from B to B prime by an amount v dt in a small time dt. It would move by a small amount v dt, isn't it? Now, A would then, this was the original line joining A and B. This would be the final line joining A and B. Yes or no? This is the original line joining A and B. This is the final line joining A and B. dt seconds later, in a small time dt, B would have moved by a small amount dt like this, right? V dt like this. Suppose in the process, the line joining A and B has described a small angle d theta. The line joining A and B has described a small angle d theta. Then, the manner in which the line AB reorients itself is given by, the reorientation is given by a rate at d theta dt. That's a small angle d theta by which the line AB has swiveled in a small time dt. The line joining A and B has swiveled by a small angle d theta in a small time dt. That means that's the rate at which the line joining A and B swivels with time, So this would be, so if A is perceiving B, if A is looking at B and is asked to compute the angular velocity of B, if A is asked to report about the angular velocity of B, then the manner in which A would report the angular velocity of B, is the rapidity with which the orientation changes of AB. The rapidity with which AB changes its orientation. That means, see, how much, to what extent has the orientation changed in a small time dt? d theta, the line joining A and B. And that divided by dt will give me the rate at which the orientation changes with time, right? The line joining A and B. Therefore, A would report the angular velocity of B as d theta dt. Would report the angular velocity of B as d theta dt if A is fixed. Yes or no? Now, this was the original length of the line joining A and B. Original length of the line joining the two particles A and B, where A is fixed and B at a certain instant has a velocity v. In a small time dt, its velocity is not going to change, right? Now, tan of d theta is how much? What is tan of d theta? V dt by L, V dt by L. Where V is the velocity of B perpendicular to AB, where V is the velocity of B perpendicular to AB, right, is V dt by L. Now, we'll be able to show. Now, d theta is a very small angle. D theta is a very, very small angle, very close to 0. Now, tan of very small angles, tan of x, if x is very small, is approximately equal to x. Tan of x, when x is very small, is equal to x. See, you can verify that. You can verify that. When x is very small, tan of x is approximately equal to x. That's a decent approximation. We will learn more so in trigonometry. So, d theta is very small. So, tan of d theta can be replaced by d theta. Tan of d theta could be replaced by d theta. So, d theta then is v dt by L, where the angles are measured in radians, not in degrees, right? In radians, tan x is approximately equal to x when x is very small. You can pick your calces, check some small values of x, and you would know that I am not cheating you. Huh? See, very close to 1, right? So if d theta is very small, tan of d theta can be replaced by d theta. Now, the angular velocity of B as reported by A would be the rate at which Theta changes with time. That means it's going to be d theta by dt. D theta by dt would give me what? The angular velocity of B as perceived by A or as reported by A. So the angular velocity of B as reported by A is d theta dt, which is V by L, where what is V? V is the velocity of B perpendicular to the line joining A and B. V is what? The velocity of B perpendicular to the line joining A and B. That's omega by omega of B as seen by A is going to be V by L. If A is fixed and B has a velocity V perpendicular to AB. Right? Now, yes, everything is in radians now. For us, angle means radians from now on, right? This. So bring this dt below d theta. So d theta by dt is V by L. But d theta by dt is omega. And this is the omega reported by A for B. The perception of the angular velocity of B as seen by A would be how the orientation of AB changes with time. How the orientation of the line joining the two particles changes with time will be the perception of the angular velocity of B as seen by A. Right? This has to be very clearly understood. Now, radians, convert this into radians, my friend. Now, suppose I have A and B and they are separated by a distance L. They are separated by a distance L. And say A has a velocity VA perpendicular to AB and B has a velocity VB perpendicular to AB. A has a velocity VA perpendicular to AB, B has a velocity VB perpendicular to AB. Right? I now want to be able to compute the angular velocity of B as seen by A. I now want to be able to compute the angular velocity of B as seen by A. So what I do is, as seen by A, it's as if A is my observer. It's as if I can pin A down. The moment I look upon A as my observer, that means fix A permanently, I would have to remedy the velocity of B. The velocity of B will no longer be VB, but will be velocity of B minus velocity of A would be the velocity of B with respect to A, right? So in an equivalent situation, it's as if A is fixed and treated like an observer, and that B is imparted a redefined state which is VB minus VA, which is the velocity state of B as seen by A, right? Yes or no? And it's perpendicular to AB, and say L is the separation. In this case, the angular velocity of B as seen by A, angular velocity of B as seen by A is going to be VB minus VA divided by L. Instead of V by L, it's going to be the relative velocity of B with respect to A perpendicular to AB divided by the separation between A and B. That's going to be the angular velocity of B with respect to A. Yes or no? Right? Shall I tune in further? Right? Now, suppose this is A and the velocity of A is VA like this, right? This is B and the velocity of B is VB like this. Now look at the line joining A and B. is the angular disposition of AB changing with time? No. Is the angular disposition of AB changing with time? No. That means, what's the angular velocity of B with respect to A? 0. 0. In this case, the angular velocity of B as seen by A or the angular velocity of A as seen by B is 0, because the line joining the two particles is not getting reoriented with time. Right? So in this case, so velocity components of A and B that lie along the line joining the two particles will contribute nothing to omega of one with respect to the other. Right? Suppose now, so far so good, right? Not a problem? No issues? This is particle A and this is particle B. Now suppose A has a velocity VA like this, making an angle alpha with the line joining A and B, and B has a velocity VB like this, making an angle beta with the line joining A and B, right? So this time the velocities are neither along the line joining the two, nor are they perpendicular to the line joining the two. So what I do in order to be able to compute the angular velocity of B with respect to A, I resolve these velocities along AB and perpendicular to AB. I resolve these velocities along AB and perpendicular to AB. So velocity of A along AB is like a VA cos alpha. Perpendicular to AB is VA sin alpha. Velocity of B along AB is like VB cos beta, VB sin beta. Yes or no? Is that all right? I now want to calculate the angular velocity of B as seen by A. Right? Now, VA cos alpha and VB cos beta, do they participate in reorienting the line joining AB? VA cos alpha and VB cos beta, do they participate in reorienting the line joining the two particles? No, they don't. The velocity components along AB are passive in the context of omega. Right? VA cos alpha, and this is what I told you a little while ago. The velocities along AB, if A had a velocity like this and a velocity like this, B had a velocity like this, then the angular velocity of B with respect to A is going to be 0. So VA cos alpha and VB cos beta are passive in the context of omega, right? So then effectively, in order to be able to compute omega, I ignore VA cos alpha and VB cos beta. I then just look at the velocity components of A and B perpendicular to the line joining the two, right? So then, what is it that I need to be doing? The velocity or angular velocity of B with respect to A is going to be the relative velocity of B with respect to A perpendicular to AB, isn't it? Did I not tell you VB minus VA by L, where VB and VA are velocities perpendicular to the line joining A and B. So this is going to be VB sin beta minus VA sin alpha divided by the length LAB. That's going to be the angular velocity of B with respect to A. Does not matter. If it is not greater, this will turn out to be negative. If VB sin beta is more than VA sin alpha, then AB will get reoriented like this. But if VB sin beta is less than VA sin alpha, this will turn out to be a negative number, then AB will get reoriented in this sense. That's the only difference. You know what I'm saying? Right? Okay, see, suppose A had a velocity 3 meters per second like this, and B had a velocity 5 meters per second like this, right? And I am trying to compute the angular velocity of B with respect to A. In this case, the perpendicular component of B is more than the perpendicular component of A, and I am trying to compute the angular velocity of B with respect to A. Then in this, the equivalence, that means I am choosing A to be my observer. B then has a velocity 2 meters per second this way? Yes or no? And this line AB will get reoriented like this? Huh? But suppose this was suppose I had a situation like this, where A had a velocity 5 meters per second like this, and B had a velocity 3 meters per second like this. That means in this case VB sine beta is less than VA sine alpha, right? Suppose this was the situation, then in this case the equivalent situation is, if I am choosing A to be my observer, then the velocity of B will not be 3 meters per second, will be 3 minus 5 minus 2 meters per second like this. That will be the velocity of B as seen by A, right? Minus 2 meters per second like this would actually mean 2 meters per second like this. Then if the velocity of B is 2 meters per second like this, do you realize that AB is getting swiveled in the opposite sense? That's the only difference. Yes or no? Very good. It's fun, huh? Can I wipe this off now? Now, like I said, if mod of RT is constant, the motion would be deemed circular. However, not to get needlessly restrictive, angular velocity is not just about circular motion. It's about any kind of motion. There could be an angular velocity associated, right? So mod of RT is constant, the motion is circular, let's say centered at the origin, and of radius r, let's say of radius. So mod RT, suppose that's r, then the radius of the circular trajectory is going to be r, right? This is the trajectory, say, centered at the origin. We will measure all our angles from the positive direction of the x-axis. O is a fixed point. This is theta, which measures the angular location of the moving point P, which measures the angular location of the point P executing the circular trajectory. And say the point P goes from P to P prime in a small time dt, right? Then it describes an angle d theta. Theta changes by a small amount, d theta. Theta changes by a small amount, d theta. R is the radius of the circular trajectory. R is the radius of the circular trajectory. At when the particle, so d theta dt would measure what? The omega. D theta dt would measure the omega. Now, if this is the circular trajectory, and when the particle is at P, One thing that you must understand as a cardinal truth of any kind of motion, if this is any trajectory that the particle undergoes, then the velocity at any point will always be along the tangent to the trajectory at that point. The velocity at any point of the trajectory will be along the tangent to the trajectory. So the velocity at P would be along the tangent to the circle at P, but the tangent to the circle at P would be perpendicular to the radius R, would be perpendicular to the radius R. So if this is O, which is a fixed point, this is P, the tangent, and the velocity of the particle, which is the linear velocity, of the particle will always be perpendicular to the, will always be along the tangent to the trajectory. And therefore, in this case, perpendicular to the radius, right? So R is the radius, right? And like I said, the angular velocity of P as perceived by O, angular velocity of P as perceived by O, omega, which is d theta dt, is given by V by R. The velocity component perpendicular to OP divided by the separation between O and P. That will give me the angular velocity of P as perceived by O, the fixed point. This is what we've done so far, right? Now, so this V, which is the linear velocity from instant to instant, will always be along the tangent to the trajectory and therefore would be deemed perpendicular to the corresponding radius at those points, right? Now, this was a particle executing circular motion. At any given instant of time, radius of the particle is R, this angle is theta, the particle is at P. What would be the coordinates of P? What would be the x coordinate of P? R cos theta, isn't it? What would be the y coordinate of P? R sin theta, right? So x coordinate of P in this case is going to be R cos theta, y coordinate of P is going to be R sin theta. Yes or no? And therefore the position vector of P, which is OP, OP is the position vector of P, right? Given by R is going to be xi cap plus y j cap, isn't it? Xi cap plus y j cap. That means xi cap, R taken common, cos theta I cap plus sin theta j cap. That's a position vector. And it's going to be a function of time. Why? Because this theta is a function of time. This theta is a function of time. So this R will be a function of time. The linear velocity of the particle will always be perpendicular, which we will also demonstrate. I'll be able to demonstrate that V is perpendicular to R. The linear velocity is perpendicular to R in this case. I'll be able to demonstrate very shortly. Now, what is linear velocity? Linear velocity is very clearly dr dt. Linear velocity is dr dt, yes or no? That means differentiating this with respect to time. Now R is a constant. So when I differentiate this with respect to time, this R will wriggle out, right? So this R comes out. It gives me d dt of cos theta I cap plus d dt of sin theta j cap. Yes or no? That's a linear velocity? Yes. Sorry?
Why is it ddt of r, vector r?
So
Because it is a radius, so it is a constant.
no, mod of r is a constant, but r is not a constant. This vector is changing with time, isn't it? Its magnitude is remaining constant, but the vector per se is not constant. Right? Is it not? Now, what is ddt of cos theta? Right, right. See, ddt of cos theta is going to be, first differentiate with respect to theta, and then differentiate theta with respect to time. That's chain rule. So, which is like a minus sine theta. And what is d theta dt? Omega, the angular speed of the particle. Right? Similarly, what is d dt of sine theta? Differentiate first with respect to theta. So, that's going to give me cos theta. And then theta with respect to time, that's going to give me omega. So, cos theta omega. Yes or no? Right? So, this d dt of cos theta, I can replace by minus sine theta omega. This I can replace by cos theta omega. So, omega will come out. Omega will come out. So, the linear velocity v then is like omega coming out. R is the radius of the circle minus sine theta I cap plus cos theta j cap. Yes or no? Okay. So far, so good. Now, I want to demonstrate that V is along the tangent. V is always along the tangent. I want to demonstrate. At least for a circular trajectory, I want to demonstrate that V is along a tangent. In fact, for any trajectory, V will always be along the tangent. In this case, if I am able to demonstrate that V is perpendicular to R, then V will be along the tangent. If I can show that V is perpendicular to R, then V will be along the tangent. Yes or no? Now, to show that V is perpendicular to R, this is the vector R, this is the vector V. When would these vectors be perpendicular to each other? If their dot product is 0. So, if I can demonstrate that V dot R is 0, then the problem is solved. Then V will be perpendicular to R, yes or no? Right? So, what is V dot R? V is R minus sine theta I cap plus cos theta j cap, that's V r omega dot r. R is this. So, this r will get multiplied with this, the scalars, dot cos theta I cap plus sine theta j cap. Yes or no? Right? Yes, so what's the dot product? Minus sine theta cos theta plus cos theta sine theta, which is 0. You then become a hero. Right? So, so this then, like I said, is going to be 0. V dot r turns out to be 0. And if V dot r turns out to be 0, that means V is perpendicular to R. R is the radial vector, which is along the radius from instant to instant. V therefore will be a tangential vector along the tangent from instant to instant. So, the linear velocity will always be along the tangent to the trajectory, as explicitly seen in a circular trajectory. Even if the trajectory is non-circular, then also the velocity vector will always be along the tangent to the trajectory from instant to instant. Got me kya? Pakka. So, V dot R0 means V must be perpendicular to R, and therefore along the tangent to the trajectory. Clear? Confused? No? Now, the magnitude of this linear velocity is called linear speed. V, as you see here, is omega r minus sine theta I cap plus cos theta j cap. Right? So the linear speed would be mod V, which would be omega r into magnitude of this. Magnitude of this is what? Root minus sine theta whole squared plus cos square theta, which is 1. Magnitude of this vector is 1, isn't it? Right? So omega r. So the linear speed V is omega r, as we saw earlier as well. V is r omega. No. Till this point, have I used the fact that omega remains constant? No, I have not used the fact. All that it shows is, at any given instant of time, if the linear speed is v, the angular speed at that instant is going to be v by r. So if omega changes, v will change, or vice versa. If v changes, omega will change, commensurate with this requirement. Right? Now, if I now said that the motion is uniform circular, till this point, there was no mention of the motion being uniform or non-uniform, right? So now if I continue in the same stride and said motion is uniform circular, it would mean that omega will remain constant, angular speed will remain constant, and if angular speed remains constant, the linear speed will also remain constant. Right? Now, even though the magnitude of the linear speed will remain constant, can the linear velocity remain constant? Can the linear velocity in circular motion ever remain constant? This is linear speed, magnitude of the linear velocity, that's remaining constant. But can the vector v remain constant in circular motion? No. Why? Because see, its direction is constantly changing. When the particle is here, its direction is here. When the particle comes here, its direction is here. At different points, you have different directions of the tangents. So the linear velocity is a non-constant vector, because its direction at least is changing. Even if I assume that motion is uniform, it only means that the linear speed remains constant, not the linear velocity. Right? This is what it means. Now, notice, so now from this point onwards, let me look at a situation where I would imagine omega to be constant and linear speed to be constant, v to be constant. If the velocity vector is changing with time, that means there is a case of acceleration. There is a case of acceleration, right? Even though the magnitude of v could remain constant, the particle will be deemed accelerated because the direction of v is changing with time, right? So the acceleration vector of the particle in this case is dv dt. That's the acceleration vector of the particle, rate at which linear velocity changes with time. That's the acceleration of the particle. That means if I differentiate this with respect to time, I'm going to get the acceleration. That means this is d dt of omega r minus sine theta I cap plus cos theta j cap. Yes or no? Now, since the motion is uniform, omega is a constant, so omega comes out of the derivative sign. R anyways is a constant, so R will come out of the derivative sign. So both omega R will come out. Now, inside the parenthesis, ddt of sine theta, how much will it be? This will be minus cos theta omega. Cos theta omega. This will become minus sine theta omega. Right? Yes or no? That's the acceleration vector of the particle as a function of time. Is it constant? No, because theta is changing with time. So this vector for sure is not constant. This vector for sure is not constant. Yes or no? This acceleration. And this would be the acceleration for uniform circular motion. Not if the motion is non-uniform circular. In non-uniform circular motion, what would happen? Omega will change with time, and I couldn't have taken this omega out of the derivative sign. You know what I'm saying? So this is the acceleration in uniform circular motion. However, this is the velocity whether the motion is uniform or not. Even if omega changes with time, then the change in v would be reflected in this equation. That's not an issue. Got me? So now the acceleration vector. Realize that I can take this minus out. So this will give me, and of course there was an omega also. That will make this omega squared r. Yes or no? There was an omega as well. When I differentiated sine theta, I got cos theta omega. So another omega which will get multiplied with this. So that will make it omega square. So omega squared, same here, minus sine theta, omega square, and the omega squared together come out of the derivative sign. Right? So omega squared r. So acceleration as a function of time in uniform circular motion is going to be minus omega squared r cos theta I cap plus r sin theta j cap. Yes or no? Hey, r cos theta I cap plus r sin theta j cap was what? The position vector r of the particle. The position vector r of the particle was r cos theta I cap plus r sin theta j cap was the position vector r of the particle. Yes or no? Minus omega squared r at any given instant of time. That's the acceleration of the particle. How about it? In uniform circular motion, the acceleration at any given instant of time would be minus square of the angular speed into the position vector of the particle. You know what I'm saying? Now notice that the direction of A is opposite to the direction of R. This is what it means. If A is minus K times B, then the direction of A and B is opposite, right? So that means, what is the direction of R? The direction of R is like this at a given instant of time. So the direction of A, so R is going away from the origin, whereas A is directed towards the origin, opposite to R. Yes or no? That means this acceleration is directed towards the center of the circle. This acceleration is directed towards the center of the circle in uniform circular motion. And this acceleration is called centripetal acceleration. This acceleration is therefore referred to as centripetal acceleration. So minus acceleration equal to minus omega squared times r at any given instant. This acceleration directed towards O will be referred to as the centripetal acceleration. This is the centripetal acceleration. So even if the motion is uniform circular, it will still be packaged with an acceleration which is directed towards the center of the circle, which will continuously change the direction of the velocity. Acceleration must either change the magnitude of the velocity or change the direction or both. In this case, in uniform circular motion, this acceleration is perpendicular to V. Do you realize that this acceleration is directed towards O? Is perpendicular to the velocity? If acceleration is perpendicular to the velocity, it is incapable of changing the magnitude of the velocity. All that it changes is the direction of the velocity. If acceleration is directed along the velocity, it will not change the direction of the velocity. It will only change the magnitude of the velocity. Yes or no? If acceleration is perpendicular to the velocity, it will only change the direction of the velocity. Cardinal truth. If acceleration is perpendicular to the velocity, it is incapable of changing the magnitude of the velocity. If acceleration is along the velocity, it cannot change the direction of the velocity. It will only change the magnitude. So in this case, it is only changing the direction of the velocity. This acceleration, centripetal acceleration, its task is to change the direction of the velocity from instant to instant and keep the velocity tangential at all instants. That's the job of this acceleration. Centripetal acceleration directed towards the center of the circle. Towards, right? The magnitude of the centripetal acceleration, this is the centripetal acceleration, its magnitude is going to be omega squared times magnitude of r, and magnitude of r will be the radius of the circle. Magnitude of r will be the radius of the circle. So this turns out to be omega squared times the radius r of the circle. That's the magnitude of the centripetal acceleration. AC, omega squared r. Omega is the angular speed of the particle, r is the radius of the circle. Yes or no? So far so good. No issues with this, right? Questions? No? Clear now? I'll come to that. Just give me a moment. Just give me a moment. I'll build that up for you. Just give me a moment. Is that okay so far? So what we have learnt in circular motion is, number one, the velocity, just like any other trajectory, will always be along the tangent from instant to instant, one. And therefore, it will always be perpendicular to the radius vector from instant to instant. Two, this velocity is the linear velocity. Its magnitude is called the linear speed. At any given instant of time, if the particle has angular speed omega, then its linear speed v would be r omega. Now, if omega changes, v will change, right? In uniform circular motion, linear speed and omega both will remain constant, right? However, the velocity vector will not remain constant. Even if its magnitude remains constant, its direction will constantly change. So if its direction is changing, that means there is an acceleration associated with this change of direction, and that acceleration comes in the form of what is referred to as centripetal acceleration. Its magnitude would be omega squared times the radius of the circle, and will always be directed from along the towards the center, and its only job would be to change the direction. In general, every time the acceleration is perpendicular to the velocity at all times, it will not change the magnitude of the velocity, it will only change the direction of the velocity. If acceleration is along the velocity, it will not change the direction, but it will change the magnitude. But if the acceleration, in a general sense, say, if a particle has a velocity v like this, in this direction of magnitude v. And if the acceleration is neither along v nor perpendicular to v, then the acceleration, suppose it is at an angle theta with respect to v, then acceleration could be resolved along v as a cos theta and could be resolved perpendicular to v as a sin theta. Yes or no? The acceleration, so a cos theta will change the magnitude of v, whereas a sin theta will change the direction of v. So in this case, both the magnitude and direction of the velocity will change. Yes or no? Shall we proceed? So, if there is a particle whose omega remains constant, then its tangential speed v will be r omega will remain constant. Tangential speed will remain constant, right? And this particle will only have an acceleration directed towards the center, which is omega squared times the radius of the circle, which is the centripetal acceleration, right? If the motion now is non-uniform circular, see, this is the story of uniform circular motion. The acceleration, the only acceleration that the particle has is centripetal acceleration. It will not change the magnitude of v. It will change the direction of v from instant to instant, this acceleration. Why? Because it is perpendicular to v. Yes or no? You know what I'm saying? Now, in non-uniform circular motion, omega changes. Omega changes with time. Omega is not constant. Angular speed of the particle, right? So linear speed v, which is r omega, r is constant, omega is changing with time. So this will also change. This also changes with time. The linear speed will also change with time. That means the magnitude of v is changing with time. That means at every given instant, the direction of v is changing, which will be obtained by the centripetal acceleration will change the direction of v. However, the magnitude of v, this magnitude of v can be changed only if there is an acceleration along v. That means there is a tangential acceleration. If there is a tangential acceleration, at, that will change the magnitude of v. So in non-uniform circular motion, you will not just have centripetal acceleration, you will also have tangential acceleration. While the centripetal acceleration will keep the circularity intact, will keep the direction of the velocity along the tangent from instant to instant, will only change the direction of the velocity. The tangential acceleration will change the magnitude of the linear velocity. That means will change the linear speed from instant to instant. So there would be, in non-uniform circular motion, there is not just a centripetal acceleration, there is also a tangential acceleration. And how does that tangential acceleration work? What does this tangential acceleration do? It changes linear speed. Therefore, it must be rate at which linear speed changes with time. That must be tangential acceleration. This is centripetal acceleration, which is omega squared r. Tangential acceleration is ddt of v. That means it's ddt of r omega. R will come out, but not omega, because omega is not constant. So r comes out, so that makes it d omega dt. But rate at which omega changes with time is referred to as angular acceleration alpha. Rate at which omega changes with time is referred to as angular acceleration alpha. So this is r times alpha, where alpha is d omega dt, angular acceleration. So if the motion is uniform circular, then alpha is 0. Alpha will be 0 and at will be 0. Right? But in non-uniform circular motion, alpha will be non-zero because omega is changing with time. And at, the tangential acceleration which changes the magnitude of the linear speed, will also be non-zero. That's a story. That means now you'll have two things. There would be a r alpha and there would be a omega squared r. Right? So in non-uniform circular motion, at any given instant of time, there is going to be a tangential acceleration, at, which is r alpha, and there is going to be a centripetal acceleration, which is omega squared r. Omega is changing with time. So at a given instant when the angular speed is omega, at that instant there is a centripetal acceleration omega squared r, and there is a tangential acceleration r alpha. Yes or no? Right? Yes, please ask.
For the centripetal acceleration, we had the assumption that the omega was constant.
Yes, but now, no. So what it boils down to is that the centripetal acceleration, look at the job of the centripetal acceleration. Its job was to change the direction of the velocity. Its job was not to tinker with the magnitude of the velocity. Now, that means the job of the centripetal acceleration was to keep the circular trajectory intact. Even if the motion is non-uniform circular, you will still have to change the direction of the velocity in exactly the same way you did earlier, and therefore the job of omega square r remains the same now. No matter what the magnitude of the linear speed is, its only job is to change the direction. Even if the motion is non-uniform circular, you would still need centripetal acceleration so that the direction of the linear velocity changes from instant to instant and is maintained along the tangent to the circular trajectory. So this will not change. But now, since the magnitude of the linear velocity is changing, you need an additional acceleration along the tangent as well. And the job of this acceleration component would be to change the magnitude of the linear speed. This will change the direction of the linear velocity. This will change the magnitude of the linear velocity. So they have their functions separated at birth. Right? Clear? Very clearly, the net acceleration of the particle in non-uniform circular motion would be given by this A net, the resultant of AT and AC. This is AC, centripetal acceleration. The resultant of AT and AC will give me the net acceleration of the particle in non-uniform circular motion. So A net, as you can see, is going to be root AT squared plus AC squared would be the net acceleration of the particle in non-uniform circular motion. Yes or no? The idea is clear, perfectly settled in your heads? Huh? Also okay? Now, let me look at non-uniform circular motion. That means non-uniform circular motion is one in which omega is changing with time. That means there is a case for angular acceleration alpha, which is rate of change of omega with time, isn't it? When I talk of non-uniform circular motion, It simply means that omega changes and the rate of change of omega with time is defined by an entity called alpha, which is angular acceleration. Right? Now I would look at a special non-uniform circular motion in which omega is changing all right, but alpha is remaining constant. Angular acceleration remains constant. Non-uniform circular motion in which alpha at least does not change with time, and constant angular acceleration alpha. Otherwise alpha could also change with time, angular acceleration could also change with time, right? But we will assume that there is this case for non-uniform circular motion in which omega changes with time, but alpha does not change with time. Constant angular acceleration alpha. That's what we'll assume, right? So I will assume that non-uniform circular motion in which angular acceleration alpha is constant. Right? But omega is changing with time. Omega is changing with time. Suppose at time t equal, so this is the particle executing this circular trajectory, say in this sense. At time t equal to 0, say theta was 0. If the particle is at p, then theta is 0 at this instant. This is my reference line that measures theta. So theta is 0 along this line. Theta is 0 and omega at this instant is some omega naught. The particle has an angular speed omega naught at this instant of time. At t equal to 0, its angular speed is omega naught. And its theta is 0, right? Now, t seconds later, the particle arrives at p and its omega is becoming omega. It would have described an angle, theta at the center, and so on and so forth, right? T seconds later, this is time t equal to 0, at an instant of time t, the particle arrives at p prime, where it describes an angle theta at the center. It describes an angle theta at the center, and its angular velocity becomes omega, a function of time, a function of time, right? Now, but alpha will be preserved. Rate at which omega changes with time will remain the same. So alpha is rate at which omega changes with time, right? So can I say d omega is alpha dt? Can I say this? Right? Let me integrate both sides. When t is 0, which is this instant, omega is omega naught. When t is some t, say omega becomes some omega, omega becomes some omega. When I integrate d omega, I get omega. And when I supply the limits, this is going to become omega minus omega naught, where omega is the angular velocity at an instant of time t. Alpha will wriggle out. Integral dt would be t. When you supply the limits from 0 to t, it will become t. So angular velocity at an instant of time t is going to be angular velocity. This is angular velocity at an instant of time t is going to be omega naught plus alpha t, where alpha is what? Angular acceleration. Draw an analogy with v equal to u plus at, isn't it? V was the velocity in constant acceleration at an instant of time t, u was the velocity at time t equal to 0, a was the constant acceleration a. Instead of this, you have the equivalent angular variables, v to be replaced by omega, u to be replaced by omega naught, a to be replaced by angular acceleration alpha, right? So omega is omega naught plus alpha t, the angular velocity varying as a function of time. Yes or no? Right. Now, can I remove the clutter from here? Now, what is omega after all? Omega is the rate at which theta changes with time, right? Omega is the rate at which theta changes with time, yes or no? Rate at which this theta changes with time would be a measure of the angular velocity of the particle. And omega at any given instant of time is given by omega naught plus alpha t. Can I say this? Right? So this gives me d theta equal to omega naught plus alpha t dt, where theta is the angular displacement at any given instant of time t. Theta is, instead of being the linear displacement, it is the angular displacement at any given instant of time t. Yes or no? Right? Got me? Let me integrate both sides. When t is 0, we assume that theta was 0, angular displacement was 0. At an instant of time t, then theta became some theta. Right? When I integrate omega naught dt, omega naught will come out. It will give me omega naught into t. Alpha is constant, so alpha will come out. So t dt would give me t squared by 2. Right? Yes or no? So this will give me theta equal to omega naught t plus half alpha t squared. And the equivalent that you have seen in S is ut plus half of at squared for constant acceleration. Right? So far so good? Right? Now, if you are done with it, can I wipe it off? Huh? Now alpha, realize, is d omega dt. That's alpha, isn't it? That's alpha. I could rewrite this as d omega d theta into d theta dt. Can I do this? But what is d theta dt? Omega. D theta dt is omega, yes or no? So this d theta dt is actually omega. So this gives me omega d omega d theta. That's alpha. Clear? Which then would mean omega d omega is alpha d theta, right? Omega d omega is alpha d theta, right? Integrate both sides. When theta is 0, omega is omega naught. When theta is 0, omega is omega naught. And when theta is some theta, omega becomes some omega. When theta is theta, omega becomes some omega. Right? When I integrate omega d omega, what do I get? Omega square by 2. And when I supply the limits, I get omega squared minus omega naught squared by 2. That's the alpha will come out. Integral d theta would be theta. Hey, confused? No. This gives me omega squared equal to omega naught squared plus 2 alpha theta. And the equivalent is v squared is u squared plus 2as. So will not be difficult to recall these, because the equivalence is set for us, right? Clear? So these are equations of motion for non-uniform circular motion, but with constant alpha, angular acceleration alpha. All's fine.